A lot of students get the idea of strong versus concentrated with acids confused. So I just want to go through what a strong acid looks like and how that hydrogen ion concentration can change, because ultimately we measure our acids by the hydrogen ion concentration, right? A strong acid breaks up completely and makes a lot of hydrogen ions. So if I put 3 molar hydrochloric acid, and this is 1 liter, it's going to break up into 3 moles of hydrogen in that 1 liter, 3 molar hydrogen and 3 molar chloride ion concentration, okay? Or I could put 1 molar hydrochloric acid into water and I'm just going to get that 1 mole of hydrogen and 1 mole of chlorine. So right now, hydrochloric acid is a strong acid. It ionizes completely, but you can see this is concentrated and this is dilute. This has more hydrogen ions. So you can see where that confusion of strong versus concentrated gets mixed up. This is the same strong acid, but we have it more concentrated here, and that's dilute. So we are going to start talking about this concept. So once again, the strength of acids is how acid or base will ionize or break apart in water. And we're going to talk about concentrations today, and then we're going to change it into the pH scale. But just a little quick introduction. Our pH scale measures how acidic or basic the solution is by telling us the concentration of the H plus ions or hydronium ions or H3O plus ions in water. So at the scale of 0, we have a very acidic, very high concentration, and we'll understand these numbers better in our next lesson. At 7, we have neutral solution based on our pH numbers, and a pH of 14 is basic. So our acidic goes from 0 up to 7, and then we call it basic if it's 7.1 to 14. And so to understand this play on acids and bases, we're going to talk about that a definition that is H plus and OH. And basically, water self-ionizes. So water turns into H plus and an OH minus, and we like to call that a hydrogen ion. But here's what I want you to know. It's an equilibrium. It does not ionize very much at all. So sometimes chemists will teach this with a huge H2O and a tiny, tiny H plus and a tiny, tiny OH. And that's because it's mostly pure water. It doesn't really break apart very much at all. Now, the other way you're going to see it's written is H3O plus OH. So later on, chemists found out that there really is no H plus in water. It forms an H3O plus, which they call the hydronium ion. So a lot of chemists still use hydrogen ions, and you'll see why that becomes more useful. But IU likes to use H3O, so I'm going to show you both, but it's the same thing, okay? The H3O, the H plus, they're the same thing. This is just what they thought it was, but it turns out it's really H3O plus, okay? So, because water ionizes and it's in equilibrium, we can write an equilibrium constant expression. Yay! So remember, liquids are not in our equilibrium expressions. Only aqueous and gaseous elements are. So our K, our big capital K, equals the concentration of our products and divided by our reactants, but that's a liquid, so it doesn't go in there. And we call this a special K. It's K, and W is for water, and it's the ionization constant for water, because these are the ions that water breaks into in equilibrium. And that number is constant. It doesn't change. It's at 25 degrees C, okay? And so if I change the temperature, it changes, but you don't need to know that at this level. And so it always equals 1 times 10 to the negative 14th. So if I know in an aqueous solution of water, if I know my hydrogen ions or my hydronium ions, I can calculate what the hydroxide ions are. Remember, we also call that H plus. So here's a little example. If my OH concentration in water is 0.01 molar, What's the H plus concentration? So I would take 1 times 10 to the negative 14th, use this formula, plug in that for my OH times H plus, and then I have to solve for H plus. So divide by 0.01, and I get 1 times 10 to the negative 12th molar is the concentration of my H plus in that solution. And so everything always stays in that OH-H equilibrium when we do anything in an aqueous solution, meaning if we do any reactions in water. So we can use this to calculate a lot of information. So some of the problems you'll be doing, and we've done this before, is understanding how things break down when I dissolve them. So when I dissolve barium hydroxide in water, I get 1 barium and then 2 hydroxides. So if this is 1 molar, my barium's also 1 molar because I got 1 mole in water. And then I have double the concentration of hydroxides. It makes 2. So if we look at this, I have barium hydroxide breaks into a barium ion and 2 hydroxides. So if I have 0.01 molar of barium hydroxide, it's going to break apart into 0.01 molar of barium, but then I have 2 times the amount of hydroxide, so that's going to be 0.02 molar. So what is the concentration of the H3O plus and the OH minus? Well, I just figured out that it's 2 times that for my OH, okay? So then I can plug it into my ionization constant for water expression, and I can solve for what the H3O or the H plus ion concentration is. Okay? Now here's why I like to say the H plus is easier to think about than the H3O. Now we're going to dissolve an acid in water, and we're going to say that it's 3 times to the negative 5th molar. What's the concentration of the H3O plus or the H plus? Remember, these are interchangeable. And the OH ions. Okay, so I didn't use brackets here, I said the word concentration. Up here, remember, if it's in brackets, it means molarity or concentration. So make sure that you get used to what those brackets mean. So my H2SO4 or my sulfuric acid will break apart into 2 hydrogen ions and 1 sulfate ion. So if my concentration before I put it in is 3 times 10 to the negative 5th, when it breaks apart, I will have 3 times 10 to the negative 5th of my sulfate because there's only 1 of them, but then I have 2 times that concentration because there's 2 H plus ions, so that's 6 times 10 to the negative 5th. So my concentration of my H3O plus, which is also, remember, it's also H plus, that's that. I'm just going to plug that into my equilibrium expression for water, my ionization constant for water, and I'm going to solve for the OH just like we did up here, only now I'm solving for OH, and I get 1 times, or 1.6 times 10 to the negative 10th. Just a reminder, I'm solving for OH. You got to divide both sides by 6 times 10 to the negative 5th. Okay? And don't worry about sig figs right here. These are just examples. There you go.